So I think this is probably going to wrap up our discussion of inverse trig functions. We're going to do just a few problems. I call these examples for class, and I have 4 problems here that we're going to work our way through. Good examples for you guys to be able to do. Some have no calculator allowed. Some require a calculator, and I'll point that out as we go along. So first one, no calculator, find cosine of tan inverse of negative 2/3. And so we've seen a couple of these composition problems before where there's a trig function and an inverse trig function. And several times we've seen how it's useful to let the output of the inverse function, which is inside parentheses in this case, give it an angle name like theta to help us work our way through the problem. So here we can let theta equal the tan inverse of negative 2/3. And our answer is going to be, our final answer for this problem is going to be cosine theta. So let's see what we can say here. Theta is tan inverse of negative 2/3. So tan theta is equal to negative 2/3. And since we're using the inverse tangent function, negative pi over 2 is less than theta is less than pi over 2. We may have to use that information along the way to help us solve. We want to find cosine theta. That will be our final result, right? Cosine of this expression, cosine theta. If we know tan theta, can we find cosine theta? And maybe I should say that our answer will be cosine of theta. Well, if you know tan theta and you want to find cosine theta, that's kind of a variation on our problems where we get from sine to cosine or cosine to sine without ever knowing what theta is. We're going to use the fact that, well, we have tan theta equals negative 2/3. I can rewrite that as sine theta over cosine theta equals negative 2/3. And we're also going to use the fact that sine squared theta plus cosine squared theta equals 1, that most famous trig identity. I'm going to take this first equation from tangent and multiply both sides by cosines. If I multiply both sides by cosine, I get sine theta is equal to negative 2/3 cosine theta. That is going to allow me to make a substitution in my Pythagorean equation where I can replace sine theta with negative 2/3 cosine theta. Negative 2/3 cosine theta squared plus cosine squared theta is equal to 1. So I made a substitution to get this equation, which came from sine squared plus cosine squared equals 1, that involves cosine theta only. So if I square here, I have 4/9 cosine squared theta plus cosine squared theta equals 1. The trick here is to realize that cosine squared theta is just 1 times cosine squared theta. These are two like terms that we can combine. We can just add the coefficients. I'm actually I'll write out what I'm going to do. I'm going to add 4/9 plus 1 cosine squared theta equals 1. If you want, it's like I factored out cosine squared theta from those two terms. 9/9 plus 4/9 is going to be 13/9 cosine squared theta equals 1. Now I can multiply both sides. Whoops, sorry. I forget that when I go below the scoop. I can multiply both sides by 9/13. In order to isolate cosine squared theta equals 9/13. And now I can take square roots. Cosine theta is plus or minus the square root of 9/13. Cosine theta is, can I make a choice of plus or minus sign? Well, we know from earlier in the problem that theta was between negative pi over 2 and pi over 2. That tells me that we're in either quadrant 1 or quadrant 4. So if we're in quadrant 1 or 4, cosine must be positive. Square root of 9 is 3. I can write that as 3 over the square root of 13. So cosine theta is 3 over the square root of 13. And actually, we're done with our problem because we wanted to find cosine of tan inverse of negative 2/3, which is cosine of what we're calling theta in this problem, which is 3 over the square root of 13. And we got it. I'm going to try to position the camera so you can get a shot of the full problem. I'm going to leave that up there for a second. There it is. Notice that we had to use that Pythagorean theorem, Pythagorean identity, to help us find that cosine of theta without ever actually using or finding what theta was. All right, now let's go on to it's a pretty heavy problem. Now we'll go into something a little bit lighter, a little bit more straightforward. Here are calculators required. We want to find the degree measure of angles A and B, the acute angles in this triangle using a calculator. This is going to be pretty straightforward. We're back to good old SOHCAHTOA. Let's see, the tangent of angle A is going to be opposite over adjacent. So that's going to be 9 meters over 4 meters. The tangent of angle B, its opposite over adjacent, is 4 meters over 9 meters. So because these are acute angles, we can express A using inverse tangent. A is the inverse tangent of 9 over 4, and B is the inverse tangent of 4 over 9, the inverse tangent of 4 over 9. And calculator is required, so I'm just going to push some buttons. And we want degree measure here. So when I go to my calculator, I'm going to put it in degree mode. I want to be in degree mode. And 9 divided by 4, 2.25 of course, And now I'm going to take inverse tangent, so I have to hit the shift key on my tangent button. I'm in degree mode, and I get that A is about 66 degrees. Now I really only have to figure out one of these this way, because B's got to be 90 minus A, right? They got to be complementary. 90 minus 66 is 24 degrees. Now just for fun, I'm going to do 4 divided by 9 and use my inverse tangent button again, and see I get 23.9. So B is about 24 degrees. There's my value for A, my value for B, and we got our quickie problem done, our calculator problem. Now we're going to go back to a much more algebraic problem, a little bit more intense. Find the exact value of the expression in terms of x with no trigonometric functions involved in your answer. We have this sine of cosine inverse of 1 over x. So this has no numerical values involved at all. We're just going to work through the algebra. But it should look a lot like the problems where we introduce our theta. So I'm gonna let theta equal cosine inverse of 1 over x. Then cosine theta is 1 over x. And let's see, I'm using inverse cosine, so theta is between 0 and pi. And what we want to find is we got to find sine of theta. We know cosine theta. We want to find sine of theta. We're going to use sine squared theta plus cosine squared theta equals 1 once again. Now, here I don't have two equations and two unknowns like a couple problems ago. Here I want to solve for sine theta, and I can plug in for cosine 1 over x, because we know cosine theta is 1 over x. And here it's more the algebraic mess that I have to deal with than anything else. So sine squared theta is 1 minus 1 over x squared. Sine theta squared is going to be 1 minus 1 over x squared. And that 1 minus x squared I can think of as x squared over x squared minus 1 over x squared, and combine those into a single fraction, right? X squared minus 1 all over x squared is sine of theta squared. And then I have to take square roots. And let's see, this is an angle that's between 0 and pi. So on my unit circle, I know I'm in the upper half of the unit circle. So I know I'm in quadrant 1 or 2. If I'm in quadrant 1 or 2, there sine is always positive. So I know sine theta is equal to positive this stuff. Now you can take those square roots separately. Actually, sine of theta is what we're trying to find. So sine of theta, look up a little bit. If I take those square roots separately, I have the square root of x squared minus 1 over the square root of x squared. not going to get zing you on this, I think, if you simplify that denominator. But technically, the square root of x squared, we should write absolute value of x for, because if x is negative, this square root is always going to come out positive. If we just wrote x there in simplifying this, it would leave a negative x when that doesn't actually occur. So officially the answer looks like this. I don't want you to get too worked up about the absolute value sign, because we haven't actually dealt with this in a lot of other problems. But I want to say just one more thing. What we're saying is sine of cosine inverse of 1 over x, so that mess of trig stuff, is equal to this expression that doesn't have any trig functions in it. We've expressed this in terms of x with no trigonometric functions involved. Okay, I'll leave that up there for a sec. And then we're going to do just one more problem, which I think will feel lighter and shorter. It's got a word problem, and it's really just a matter of drawing the picture correctly, and then we should be okay. Oh, actually, I give you the picture. I think it's interpreting the word problem. So calculator required, so we're back to calculator use. A straight trail leads from the Alpine Hotel at an elevation of 8,000 feet to a scenic overlook at an elevation at 11,100 feet. The length of the trail is 14,100 feet long. What is the inclination of the trail? That is, at what angle does the trail rise from the horizontal? And I'm kind of showing you right there. We're trying to figure out that angle in the picture. Let me get a little tighter here. There we go. We got a little sharper picture, I think. And so let me just redraw this triangle, which is where the essential information is. So we're trying to find this angle, call that theta. And degrees is going to be fine here, by the way. But if you gave me radians, just say radians, that would be fine. I'm going to use degrees. Now, the hotel is at an elevation of 8,000 feet, and the overlook is at an elevation of 11,100 feet. So the overlook is up here, right? And I think you got to have this idea that somewhere is sea level, way down lower than these mountains. This elevation of the hotel is at this like horizontal level above sea level, and that's at 8,000 feet. The overlook is at 11,100 feet. So this side of the triangle is going to be 11,100 minus 8,000, 3,100 feet. So yeah, there's that little bit to figure out in the problem. The length of the trail is 14,100 feet long. That's the hypotenuse of this triangle. The other side we don't know at all. I guess we could figure it out with the Pythagorean theorem if we really wanted it, but I don't think we need it. This is basic SOHCAHTOA again. I have the opposite side and the hypotenuse, so I'm going to use sine of theta. Sine of theta is opposite over hypotenuse. Sine of theta is 3,100 feet over 14,100 feet. Okay, so not too bad. And the idea here is to find theta we can use the inverse sign. On our calculators, the inverse trig function buttons just take us from a value of a trig function back to the angle, right? So let's go to calculator. I'm going to make sure I'm in degree mode. I want to be in degree mode. 3,100 divided by 14,100. Okay, so some decimal I have there. Now I'm going to do inverse sign. So here I have to hit my shift sign button, and I get theta is approximately 12.7 degrees. Okay. All right, so let's see if I can do this a little better. Just get one shot with the statement of the problem and the solution all in one picture. And we're going to move on to other things. So this is the end of my lecture material on the inverse trig functions.